experimental mathematics seminar is about my favorite theorem in enumerative combinatorics. There are lots of enumeration problems that are impossible, that nobody knows how to prove. That's why enumeration is so difficult. So and there, forget about ugly. It's intractable. My favorite is self-avoiding words. So suppose you're walking on the lattice, on the two-dimensional Manhattan lattice, and you have n steps. So if you're allowed to go right, left, up and down with no restriction, the formula is easy. There is a nice formula. 4 to the power n, the number of walks. So forget about self-avoiding walks. The number of walks with n steps is exactly a beautiful formula, 4 to the power n. But it's not terribly deep because the proof is trivial. There are n independent decisions, up, down, right or left, 4 times 4 times 4 times 4. So that's an example of a beautiful explicit answer to an utterly trivial problem. But if you do self-avoiding walks, in other words, you insist that when you walk in Manhattan n steps, you never return to a previous place. So you can go up and down, but you cannot come back to exactly where you were. How many such steps are there? So if you call it A of n, nobody has any clue. There's not even an ugly formula. You'll be very, very famous if you can find an algorithm. Forget about an algorithm. You'll be very, very famous if you can find this number, A of 1000. How many very innocent, conceptually trivial problem, the number of self-avoiding walks with 1000 steps in the two-dimensional Manhattan lattice, where you go up, down, right or left. So all you insist never to come back to where you were before. Nobody has any clue. It's a number, you can easily, a computer, if you knew the number, you can easily write it down. The total number is 4 without the self-avoiding restriction. It's not a very big number for today's computers. It is, sorry, not equal. It's equal to 2 to the power 2000, which is roughly 2 to the power 10 to the power 200, which is roughly, so equal to, sorry, roughly 10 to the power 600. It's just a number with 600 digits. So it's easily you can write on a computer over one screen, even less, if you knew it. But nobody has any clue. So this is and probably it does not exist in algorithm. That's a very deep problem. So this is interesting, but also not interesting because it's hopeless. But the nice things are things that you have a nice explicit formula for a non-obvious reason. So my favorite theorem is the 3 to the power n theorem. And it's so easy to state. It was discovered by Viennot, Xavier Viennot, and his student Dominique Gouillot-Beauchamp around 1984, 1985. It's so simple to state, and the theorem is really, really beautiful. So you have domino pieces, and you arrange them in such a way, you make a tower of dominoes, and the rule is that you can put any contiguous sequence of dominoes, and once you decide, so it has to be contiguous, the bottom floor. But once you have it, the rules are simply that they have to be like this. This is not allowed. You cannot have one on top of the other. But this is okay, and this is okay. So you make thousands of dominoes, for example. And this, and sorry. So this would be okay. So let's draw. Let's draw two examples. So that's one out of the many towns of dominoes. That's one. The other one is so it has to be to meet in the middle. So this Viennot calls it heaps, but I like domino towers better. Any question?
What does N stand for now?
Oh, the number of pieces. Sorry.
So if there's only one
No,
piece,
it's
then-
N plus 1. So no, I didn't finish yet. I'm not telling you what it is. So the theorem, the number of domino towers with N plus 1 pieces is exactly 3 to the power N. For example, if I have 5 pieces, and I say, so we have exactly 81 things like this. So if you go to my website, you have a list of them. Here's the 81 of them. So it's amazing. It's very simple to state, but there's no reason why this would be exactly such a beautiful formula.
So the contiguous requirement is only for the bottom?
Only for the bottom. Once you go, you can do any crazy way. So the condition is, this is not allowed. You cannot have this on top. It has to be. So the condition, the formal condition is, if this is a piece in some floor, above it, this is okay. Or this is okay. You can either one on the left, one on the right, or both. All of them okay. But this is not allowed. You cannot have right. So with this rule, and I was trying before to draw, and for n equals, n equals 0, it's 3 to the power 0. N equals 1, it is 3 to the power 1. And then finish n equals 2. This will be so 1, 2, 3, 4, 5, 6, 7, and 2 more. Okay, the 1 is just 3 pieces at the bottom. And then you have, I forgot one.
Yeah, the second from the top has to be mirrored.
Yeah, yeah.
This.
Yeah, mirrored, make it vertical.
Oh yeah, the mirror image. I like the mirror image. Yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Exactly. It's a miracle. It's amazing. And the first proof of this by Viennot and his student Guillaume Beauchamp was extremely, extremely complicated. Like 10, 50, I don't know. It was a bijective proof. But the common conventional wisdom is bijective proofs are nice. But this is an exception. His bijective proof was the ugliest proof. Besides bijective proofs, we don't need any algebraic or analytical proofs. It was an awful, awful bijection. And they admitted it. And because they were not happy with the proof, so the proof was a bijection with words. So words with the alphabet, that's a natural thing. 1, 0, minus 1. So the natural thing counted by the 3 to the power n are words in the alphabet 1, 0, minus 1 of length n. So the natural bijection is input a word of length n and output one of these guys. And indeed, that was a proof. But the bijection was so ugly, so ad hoc, and I don't have to worry that has a fit. And then Viennot introduced this, what he called heaps of pieces, empillement in French, and it's really domino pieces. But even then, it was still complicated. And the two of the disciples of Viennot, Betrema, to make sure with the accents, I never know the accents in French, which way they go. Betrema. Yeah, it's the usual way. Okay. So Jean Betrema and Viennot, two disciples from the École Bordelaise, they found the proof from the book of this. A proof that if you sketch it, you can do it in a few minutes. And that's my goal in this talk, to have a self-contained proof of their proof of this amazing result. It's not really a bijective proof, but it's a beautiful algebraic proof.
How do you store these things in your computer? Do you use their word system?
Oh, very good. Very good question. Indeed, everything, I wrote a paper, it's in my website, is the amazing 3 to the power n theorem, and it's even more amazing proof, and the same title as this. And I have a whole computer program that has everything implemented. So, no, initially, a good question, Jake. You just do the national data structure. So you do 1, so this is 0, 2, 3. So just list the beginning of every row. So that's I store them. And later on, indeed, is the projection. Indeed, that's the novelty of this paper that I want to talk about. If you look at the proof, it's algebraic proof. And if you bijectify it, you get probably you get a nice projection. And between this and this. And I may indicate it time permitting. But now let's go to business and tell about the beautiful proof. So first, I don't like the name heaps of pieces. So in honor of Xavier Viennot, I call such a tower Xavier. So this is an example of a Xavier. So I made up a new terminology, and Xavier Viennot did not object, so I still keep it. So Xavier is anything, any tower of domino. We have anything in the bottom, and then you build on top of it according to the rules.
So it's also allowed to have holes.
Yeah, sure. In upper floors, yes, by all means. All these things they cannot collapse. So, I mean, not like this, but yeah. So you can have holes by all means. So this is a Xavier, but this is a special Xavier. So then, a subset of the Xaviers, the one in which the bottom floor has only one piece, is called a pyramid. So you have the set of Xaviers, which is called capital X. Then we have the set of pyramids that have only one piece at the bottom. That's what's called a pyramid. And then some pyramids are called half pyramids. If nothing sticks out to the right, it's called a half pyramid. So you have these three combinatorial objects. that yes is everything, then if the bottom is only one piece, it's called a pyramid. And if, so this is not half pyramid, because it sticks out to the right. And neither is this. So in this case, oh, neither is this, sorry. So that's a half pyramid. Is that it?
The mirror.
And it's mirror image, yeah, and the mirror image of this, yeah. And the mirror image of this. So we have two half pyramids. So we have 9. For n equals 2, we have 9 Xaviers, 4 pyramids, and 2.
5.
Oh, sorry, 5. Thank you. 5 pyramids and 2.
Dr. Lee, what do you mean by it doesn't stick out to the right?
Yeah, so here it doesn't stick up to the left, sorry. No, it does not stick up to the left. Everything to the right. If you look at the imagine at the line from this one.
Oh, okay. From the
So
left
that's
side
not
or
good.
the bottom?
Yeah,
Bottom.
yeah. So here, this is not good because it sticks to the left.
Okay.
By symmetry, you could, say the same thing for the right.
Yeah, sure.
I just wanted to
Either.
understand the first one.
Sure. No, thank you. Another half pyramid. Yeah, of course, arbitrarily you decide. Of course, you can have left half pyramid and right half pyramid. But let's take for the sake of convenience, a convention. And now, there's something very important, a concept in enumerative combinatorics, weight enumerator. So we assign a weight, a z to the power, the number of pieces. So the weight enumerator of, you look at the infinite set. So let's consider the following generating function. Sorry, this is a fancy x. Script x. It's a set. And now, the capital letters is a so-called weight enumerator. It's like naive counting, but instead of doing 1 plus 1 plus 1 plus 1, it's z to the power the number of pieces. And now it's a formal power series of all the pieces. So this way we can sum over an infinite quote-unquote set and get it. And analogously, we have the generating function for all pyramids, P in same thing, okay. Number of pieces of P, and H of Z is the weight and sum of the weights. And the statement that the number is 3 to the power n plus 1, where is it? 3 to the power n is the generating function. What we have to prove is, in using generating functionology, is z over 1 minus 3z. Because the coefficient of 3 to the power n plus 1, if you know your geometric series, is to the power n. So that's equivalent. So the way we prove the 3 to the power n theorem is to prove that this generating function, because if you take a coefficient of anything of z to the power 100, you collect everything, all the number of Xaviers with exactly 11 pieces. 10 pieces. So, because if you expand it by the geometric series, with others, it's 3 to the power n, so 3 to the power n plus 1. You get it. So that's really what we have to prove. And that's how the proof goes. So how does the proof go? You first know H. You analyze H. How does a typical half pyramid look like? Let's look at the anatomy. It's an anatomy of a half pyramid. Let's dissect it. It has a grammar. Every half pyramid can be decomposed into smaller half pyramids, usually. But let's look at the typical half pyramid. So here is a grammar of the language of half pyramids. It is a and one piece at the bottom. That's a half pyramid. Or it's a strict half pyramid. If it's a strict half pyramid, it means nothing is even touching this. So an example. An example of a strict half pyramid. Oh, sorry. Yeah, okay. Oh, yeah. Oh, yeah. No. It's still okay. Oh, sorry. That's okay, right?
Yeah.
No.
No?
That's the line.
Okay, okay.
Just leave it like that.
Okay.
Just leave it like that.
Okay, yeah. So this is a strict half pyramid. And let's look at the weight enumerator. If it has a singleton, it is that. So it. But if it's a strict half pyramid, if we remove the bottom piece and put the reference line, the y-axis here, we get that's the typical half pyramid, not strict anymore. But by removing this, we increased the weight by 1. So we have this correspond to z times 8z. The weight enumerator of a strict half pyramid is this, and we remove it, times any half pyramid. And vice versa. If you have a half pyramid, to get a strict half pyramid, all you have to do is move it 1 unit to the right and stick the bottom piece. Finally, what if it's not a strict half pyramid? If it's not a strict half pyramid, if you look at the y-axis, sooner or later, there is a piece that touches the y-axis. Possibly more. There could be several of them. And so on. But there is one, the lowest one. So if it's not a half pyramid, this one, that is the lowest one. Look at the one, this lowest one. Look at everything above it. So we have and it's very possible that it, so there may be some stuff here, so it could be something very complicated. And then it could be something on top. Sorry, it's not a very good picture, but and there may be some gaps. Anyway, if you take everything above this piece, you get a brand new pyramid. And if you remove the thing above this piece, and you remove this, you get another half pyramid. So if it's not a strict half pyramid, it's naturally you have 2 half pyramids. And they are completely independent of each other. And vice versa. So you have 8z times 8z. So the weight enumerator, the sum of all the weights, the generating function, is called of half pyramids, satisfies this functional equation. Yeah, Matthew?
So what would happen? Or did you allow like the pyramid to like join up, like at the top? And if so, how would you?
It could be some gaps between it. They could intertwine.
Okay.
So sorry, it's not a good picture. I'm a terrible drawer.
Okay.
So I won't even try.
No.
But the way to do it is you look at the one. If it's not a strict half pyramid,
okay,
sooner or later there'll be the lowest. There'll be one that touches the y-axis.
Okay.
So let's look at the lowest.
Okay.
Look at all the pieces right above it. Then right above these pieces. And right above these pieces, and recursively.
Okay.
And
Okay, I see.
so this automatically perform a half pyramid on right. And if you delete it, you get a strict half pyramid. So if you take this, you get so you get naturally two half pyramids in this case. Now, if you are very, very sophisticated advanced mathematician and you have an education of 9th grade, you would know how to solve this quadratic equation. Or if you live in Babylonia, 3,000 years ago, was a very big invention, the quadratic equation. So you solve it for h. So you have something with radical, but I hate radical. This is too advanced for me. I don't want to use it. Because this is not radical, that's rational. But you could find it. But if you attempt it and you like quadratic equation, go ahead, solve it, and even you can do the maple. If you forgot, you can just go to maple, you do solve, and maple would know. You do solve. So once you have, so you already have the theorem. The generating function is some ugly radical. If you like radicals, then you have the explicit expression for the generating function, but not so nice for the numbers themselves. So you go to maple, you do solve, h equals z plus zh plus zh squared, comma h. Maybe know how to solve the equation. And then you do Taylor. So you get two solutions. So you do percentage I means previous thing. 1 z equals 0. I don't know, 31. You look at the coefficients, you copy and paste, you go to Sloan, you get that this sequence is a well-known sequence. Some numbers, but never mind what are. It's a famous sequence. So this is how to count half pyramid. And if you're really impatient, you can solve the quadratic equation and find out the names. But I'll spare you. My point is, you don't need radicals. Now we're ready to tackle pyramids. Let's look at the anatomy of a pyramid. So for a pyramid, it can stick to the beyond and to the left of the y-axis. So let's look at the typical pyramid and see how it looks. So this, for example, so this is not a half pyramid because it sticks to the right. That's not a very good example. So let's do this. If it's not a half pyramid, sooner or later, look at the first lowest piece that goes way beyond the y-axis. And let's look at everything above it. See, this is the lowest piece. It's a pyramid on its own right. And if you remove it, you get a half pyramid. Because everything that goes to the left of the y-axis must be on top of this one. So we have another equation. Every pyramid. Of course, it could be a half pyramid. A half pyramid is a pyramid. So every pyramid is a half pyramid. But if it's not a half pyramid, then there is the lowest piece that lies strictly to the left of the y-axis. Look at everything above it. It's a pyramid on its own right. And once you remove this pyramid, you get a half pyramid. They have the following linear equation. Since we presume you already know H, if we knew how to solve a quadratic equation, you can solve for P. Okay?